In this video, we're going to talk about an indefinite integral that we want to evaluate. The integral of 7 divided by the function 4x squared plus 9. So first off, it's a good idea to kind of know what type of function that you're trying to integrate. And this is a rational function that we want to integrate. It's a polynomial divided by another polynomial, and that's called a rational function. And in general, there's lots of different techniques and things that you might have to look at. But in this video, we just want to focus mostly on how you would do an integral of this type. And so the things that I show you here will work for integrals of the form a over ax squared plus b, where capital A is a non-zero real number, and a and b are positive real numbers. So that's important that because you don't really want to apply these techniques to functions that are different from that. In particular, if b were a negative number, then the techniques that I'm going to show you here, you wouldn't want to apply that to those. So make sure that you understand that that what I'm going to show you here is just for this type of integral, where I have a number, right, over ax squared plus b, where a and b are positive real numbers. Okay, and then the other thing that you're going to have to remember is one of the derivative facts, the one about tan inverse, right? And that is that the derivative of tan inverse is 1 over x squared plus 1. So the antiderivative of 1 over x squared plus 1 is tan inverse, right, plus some constant c. Okay, so, and the general idea of this is we're going to use the following substitution. So this is just really an integration by substitution problem, although kind of different from the beginning ones that you study maybe in a Calculus 1 class. So the basic idea is that we are going to use this substitution, right, and that's going to be the square root of ax equals the square root of bu. And we're going to make that substitution and change the original integral into some expression involving this integral right here. And that's what we just mentioned with the fact about tan inverse, that the integral of that is tan inverse. All right, so here's how we would go about it. So starting with the original problem, in our case, the substitution is going to be the square root of 4x equals the square root of 9u. And so at first, when you look at that, you might not think it would work, but it does turn out to work, right? And in fact, what it will do is transform this integral into this one here, or one involving that integral right there. In this case, the numbers are pretty nice. They're both perfect squares, so you would get just this simplification: 2x equals 3u. All right, and that's the substitution that you're going to need for this problem. So once you have the substitution, right, then what you want to do is calculate your du. In other words, take the derivative of both sides. So the derivative of 2x would be 2, and then put dx, and the derivative of 3, right, u would be 3, and then put du there. All right, so again, we're just proceeding by integration by substitution. All right, so looking at the integral, though, a couple of things to notice is that, number one, we don't have a 2x explicitly in here. You can kind of make this so that it's a 2x. So if you see that possibility, then you can go ahead and do that. And then also have dx in here. I don't really have 2dx. And so what I'm going to have to do is to adjust both of these, right, and to make it easier to substitute. So first thing I'm going to do is just solve for x. I have the original substitution, 2x equals 3u. And I can solve for x just by multiplying both sides by 1/2. So I wind up with x equals 3/2 u. And now that's just going to make it easier to substitute. Everywhere I see an x in the integrand here, I'm just going to substitute 3/2 u. And then I'm going to do the same thing for dx, right? Well, I have 2 dx equals 3 du. So again, I'm going to multiply both sides by 1/2. And that will give me dx equals 3/2 du. And so that, again, is going to enable me to make the substitution a little easier I can just substitute 3/2 du for dx. Okay, so now we are ready to substitute, and what we need to do, right, is to change every single occurrence of x over to u using the original substitution and the du that we calculated. All right, so there is our original problem, and here we are going to substitute 3/2 u for x, and then dx, we know that that is exactly equal to 3/2 du. All right, so we have switched every single occurrence of x over to some equivalent expression involving u, and same thing for the dx as well. All right, and now what we're going to do is to simplify this as much as possible and then see where we're at once we do that. So the first thing I'm going to do is to remove the 3/2. It's a constant, right? And so the constant multiple rule says I can just rewrite the constant and multiply by the integral of this expression here. So I can pull the constant out. I'm going to do the same thing with the 7 up there. I'm going to pull it out, and then 7 times 3 will give me a 21 over 2. And then the other thing I did here was to go ahead and square this factor here. 3/2 squared. Oh, I'm going to do that in the next step, rather. Sorry, jumped ahead of myself. And there I go ahead and do it. 3/2 squared is 9/4. And then u squared is u squared there. Okay. So square that out. Then here I have 4 times 9/4. That would just give me a 9. So one of the critical things that happens is that in these problems is that the number here that was originally with the x squared should cancel, and then leave these two numbers to match right here, the 9 and the 9. And since those two numbers match now, the bottom part has a common factor, and I can factor that out like so. And now you can see, hey, look, that looks a lot like the derivative for of inverse tan, and so it's getting closer and closer to something that we already know how to integrate. All right, and then finally here we have this constant 9. Again, the constant multiple rule says that I can just bring that out in front of the integral, and then 21/2 times 1/9, just reduce that down to 7/2 times 1/3, which comes out to be 7/6. All right, and so now everything is pretty much completely simplified, and our substitution worked, right? It boiled the original integral down to an integral that we know how to do, right? We know that that is just the tan inverse. The antiderivative of 1 over u squared plus 1 du would just be tan inverse of u. And so we have the antiderivative. Now, the only thing is that the original problem, the variables were x, and what we need to do is to express this in terms of x as well to complete this problem. So what we're going to do is back substitute. And so to do that, what we would need to do is to solve the original substitution for u. So our original substitution was 2x equals 3u. We want to solve for u. We can do that by multiplying both sides by 1/3. And that gives us u equals 2x over 3. Okay. And so that's going to make the substitution easier. All we need to do is, or the back substitution rather, all we need to do is to go back and replace u by 2x over 3 everywhere it appears. There's only one spot, and so here we are with the final answer. We have 7/6 tan inverse of 2x divided by 3 plus some constant c. All right, so that's the technique for integrating functions that look similar to this one in this example here, subject to those conditions that I mentioned at the beginning. There is one other note. This problem can also be done using trigonometric substitution. So you may or may not have seen that technique already by the time you watch this video. And so it can be done with that technique of trigonometric substitution that you normally see in a Calculus 2 class. The one thing about that is, in my opinion, it's more difficult to do it that way. It's a little bit more involved using trigonometric substitution. You can just use regular substitution, which is a technique that you generally see in Calculus 1.